The speaker is Joseph Grant from East Anglia, and the title is Higher Preprojective Algebras and Higher Zigzag Algebras.
Thank you. So first of all, I want to thank the organisers for the opportunity to speak here. This is a very nice conference and I'm very happy to speak. So I'm going to say lots of things related to a lot of the talks we've heard today. So the advantage of coming after all these talks is that hopefully you've seen a few of these ideas before, so I have this advantage that maybe they'll make more sense if they're new to you. The disadvantage is I might repeat some things, so please forgive me if I tell you one or two things you've heard already today. In particular, I might draw some of the same pictures you've seen. So I should say that large part of this talk are joined with Osamu Iyama, who you heard speak this morning. So I should start by fixing an algebraically closed field, which we can just be the complex numbers for today. But I'll probably write K because I'll get confused if I try to write C instead. Okay, so we want to look at preprojective algebras. So maybe we start from G, some simple graph. And from this we can form some algebra pi, which is the preprojective algebra. And as I think you heard this morning, there's, instead of going directly from here to here, another way to look at this is we go via another algebra, which is lambda, which is the path algebra of some quiver. So where here Q is an orientation and a cyclic orientation of my graph G. Okay, so I can pass my graph to some orientation and then create a path algebra, and then from there I can create something which I might call the preprojective algebra of my algebra lambda. Okay, so let's have everyone's favorite example, which is A3. So let's have lambda to be the path algebra of 1, 2 to 3 with alpha and beta. So we concatenate paths if possible, and if not possible, they're 0. So alpha beta here is non-zero, but beta alpha 0. So this is an algebra that's much smaller than I think some people like to think about. This is really a 6-dimensional algebra, and it's non-commutative, you can see. So this is non-commutative, dimension is 6, and it's not semi-simple. Okay, we have extensions of simple modules by other modules, non-split extensions.
Just to be clear, what's a simple graph? What's the adjective?
Sorry, I mean no loops or double edges. Thanks, that's, this means no loops or double edges. Thanks.
For simplicity.
Nothing to do with simplicity of the algebra.
So
it's not necessary. It's not a necessary assumption for what you've said so far.
probably not, but I want to make sure that I don't fall into any traps. Okay, so this is not semi-simple, and there are, it has 6 indecomposables modules, and we know we have this Kroll-Schmidt theorem because we're in the nice finite-dimensional algebra. So all indecomposable modules, all finite-dimensional modules are just direct-sums indecomposables. Okay, so we understand if I can write down these 6 indecomposables, and I can, then we understand all the finite-dimensional modules. But we don't want to understand the whole module category, so we also want to worry about more. Okay, so just as we can break up our representations or modules into these indecomposables, we can break up our morphisms as compositions of some sorts of irreducible morphisms. I'm not going to define this, but this is something like you think it should be. And these fit into certain short exact sequences. So we have some extension of m by l, extension of n by l. So l injects into something, and that projects into n. We might have various things in the middle. And these two maps are going to be irreducible, or all these maps are going to be, all these maps into each mi are going to be irreducible, and so are these. And then we're just going to introduce some notation. So if we have L and M, this determines, in fact, if we have L, this determines M. I'm going to call this tau minus of L. This I'm going to call tau of L. And so these are the Auslander-Ruyten sequences. And this tau is meant to be the Auslander-Ruyten translation.
Tau of n?
Sorry?
You have tau of L equals L. You want tau of n.
Oh, sorry, yeah, thank you. Okay, so the example that I think we saw this morning is if I really draw out this, these sequences, then okay, I certainly have projective modules. For my algebra, I have one for each vertex of my quiver, and with my conventions, if I have an arrow from 1 to 2, then I have a map from P1 to P2, and so on. And I said there were 6 indecomposables, so there should be 3 more things, and they turn out to be here, here, and here. And okay, this is some short exact sequence, and so I can call this tau minus P1. I can call this tau minus of P2, and this is tau minus applied twice to P1. Okay, and now I want to apply some sort of orbit construction, which should make a bit more sense in a second, where I want to identify the orbits of tau minus, and so I just get these 3 objects. And then I want to look what maps I have. Well, I still have these maps going up in this direction, but I also now have maps, say, going from P3 to tau minus of P2, and I have from P2 to tau minus of P1, and I get some morphism here, and these have some relations which come from this description of my category, and this gives me the preprojective algebra. Okay, so this is pi, or pi of my A3 graph. Okay, and we've seen that we can really write this explicitly. This was the original way they were defined at sines. I can really take my graph alpha and beta, and I have some arrows in the opposite direction, with alpha star and beta star, and now I just add some relations. So from 1 I can go to alpha and then alpha star, and make this 0. From 2 I can go beta and beta star, or I can go alpha star then alpha, but then because I do a star first I put a minus sign in. And then from 3, I can do beta star beta. And if I'm being really precise, I should put a minus sign here, although of course it doesn't matter. Okay, so, and I should say, so a module M is preprojective if tau I of M is projective. For some non-negative. Okay, so this is how you construct the preprojective algebra starting from your algebra. So, yeah, I take a much more algebraic perspective on this than some people here, I think. I should say this is, so they were originally Gauss and Ponomarev who did these algebras, and then this interpretation was by Geigel and Lenzing, and then to show that these things are compatible, this is Ringel and Calabi-Yau. And we want to look at why this works. Why can we do this nice construction, and why are we just starting with lambda to be the path algebra of a quiver and not just an arbitrary algebra? So, path algebras of quivers have global dimension at most 1. So if we take projective resolutions of simples, there are at most 2 non-zero terms, they're minimal. And this, in fact, implies that this tau 0 isn't just a function between my indecomposables, it really is a functor going from the module category to the module category. Okay, so now we know this is a functor, this orbit construction makes sense. This is a reasonable thing to do. And it's worth mentioning that this might seem like a strange thing to define these preprojective modules, because I said there were 6 modules and they're all preprojective here. Well, you probably know this already happened. This happens in the Dinkin case. Okay, so note every module is preprojective precisely when KQ is a finite type. By which I mean there are finitely many indecomposable modules up to isomorphism. And like Gabriel's theorem for quivers, we know that this is when Q is an ADE Dinkin graph. Okay, so this is a nice theory, but the naive way to do this in higher global dimension doesn't work, because in general, tau minus is not a functor. So, let's go over here. So, a way to get around this was sorted out by Iyama in this century. This also works well. We have some higher global dimension. So again, I think you heard about this morning. So finite global dimension under some extra assumptions. Okay, so this notion of finite type should be replaced by the existence of a D-cluster tilting object. I'm not going to define this, but we're not going to really need this for this talk. And in general, there's a notion of D hereditary, which is due to Hirschhand, Iyama, and Opperman. And this is roughly some X vanishing condition. Certain extensions are all split. Okay, and then you can define, Iyama defines this functor now by, you just apply the usual inverse AR translate, but first you take some cosyzygy, and then you really do get the functor from the module category, as long as you have this D hereditary condition. Okay, so then we can define preprojectives. Okay, just based on. So now I just put a little subscript D, but otherwise it's the same. Okay, so there's the definition of preprojective or higher preprojective modules. And because this is a functor, we can define the preprojective algebra of some de-hereditary algebra lambda. Okay, so an important example is these higher type A cases. So starting from the ordinary type A, you can construct these other algebras, which I'll denote as lambda ds. And d is the global dimension. This is the same d from over there. So, for example, if we look at lambda 2, 3, then we can draw some sort of 2AR quiver. Here we have, this is the AR quiver up there for our path algebra of our quiver. And now we can, so now, here's some, so this is the quiver of some algebra with some relations. So this is just like I drew on the left here, I drew the quiver between my projectives. But now we can ask what are the preprojective modules for this, and you'll find that you get TOR2 minus P1, TOR2 minus P2, TOR2 minus P3, and we even get a TOR2 minus 2 P1.
So is this thing, this left thing, is the quiver in relation to the high prime, is that?
Yeah,
The mesh relation.
I should write this down. This is it's the Auslander algebra of this, so it's it's just this quiver with the relation, the commutativity relation and the zero relations. Okay, so I have maps from there to there, and there to there, P2 to TOR P2, and 3. Okay, so this is sort of how to do the representation theory of this very nice higher type A algebra. And we'll see in a bit how to get the preprojective algebra. And I can do this for any finite integers, finite positive integers DNS. You can make something out of triangles and tetrahedrons. This was, these were some of the first examples given when this higher AR theory was invented. Okay, so this is nice.
So you mean red arrow is tau 2 or tau 2 minus or?
What am I?
Yes, you need an arrow from yeah.
These are meant, the red arrows are meant to be irreducible morphisms.
Irreducible morphism, then it's a bit strange. So you
Oh,
don't
like
have- yes.
Am I meant to take these
yes,
three instead?
exactly. Yeah.
Yeah.
These three should be moved.
Copy here. I'm taking the wrong subtriangle of my triangle. So I should really have this one, and then this one. Thank you. Okay, so this is nice, so we can do this. But there's a disadvantage that it takes some work to do this sort of higher standard writing theory on our algebras. So when we just have the classical preprojective algebras, we could just write down a quiver and some relations, and it'd be quite nice if we could do that in general. So can we just write the preprojective algebra directly as some KQ prime of I prime? And yes, we can. So we've seen superpotentials before. So in the classical case, I can take alpha beta, alpha star, beta star, and you can define some superpotential, which is alpha star plus beta beta star, and then you can differentiate this at the vertices. So if we do differentiate E1, then I need to find where an E1 is. And there's an E1 hidden before alpha because alpha starts at 1. So if we get rid of that, we just get alpha star. And there's no E1 anywhere in here because these go between 2 and 3. Similarly, del of E3, W is, okay, now there's an E3 sitting between beta and beta star because beta goes to 3. So we want to swap this round. So this introduces some minus sign. So this is the super in the superpotential. We need to introduce some minus signs when we do some rotations. And you can see, if you understood that, then you can see that we're going to get minus alpha star alpha plus beta beta star when we differentiate at the path of length 0 at the vertex 2. Okay, so we'd like to be able to do this in a higher case, and we can. So this says if we have lambda, which is a quotient of the path algebra by an ideal, and it's D hereditary. So I haven't told you what that means, but in particular it means certainly that the global dimension is D. And I also want to assume that it's a causal algebra. So this, we're not sure if this is necessary for the statement, but this is certainly necessary for us to prove it because the homological algebra can be difficult and causal makes things easy. So in this case, we can write down the preprojective algebra of lambda as some KQ bar over some relations coming from a superpotential. So I now want to differentiate not by the path of length 0, but by the paths of length d minus 1. So this is in some q bar, but paths of length d minus 1. Okay, so I need to tell you what q bar and w are. And q bar is just what you think it should be. It's q, but we also have some extra arrows, which are exactly the arrows coming from pi to minus d of pj. And w is some superpotential. So to get this out, you do have to look at some of the homological algebra, but it's not that bad. I'm not going to write down details, but ask me if you want to know. I am going to do an example though. So okay, so example. Let's take the preprojective algebra of this thing I wrote down over there. Trying to use a consistent numbering. So we get something that looks a lot like we've seen already. So we have two different types of points. And this looks like something that might come from a diamond model, but it's not. I don't know, this is a different type of algebra. Okay, the superpotential is just what you guess it might be. Okay, we take the sum of all cycles going around these black vertices and take away some going around these white vertices. Okay, and now if you differentiate by a single arrow, because arrows have either 2 minus 1, then you'll get all the relations for this higher preprojective algebra. Okay, so for example, if I differentiate by this arrow going to 2 to 3 on W, this will give me 3, 1, 2 minus 3, 5, 2. So it says that these things are equal. So in fact, we get something slightly stronger. Basically, as long as we have global dimension D, then and Kazul, then all the new relations come from a superpotential. The D hereditary assumption is necessary to show that we can actually get all the original relations that lambda already had back. Okay, so now I want to restrict to some finite type cases. Okay, so this means classically ADE Lincoln, or I mean generally the existence of D plus the tilting object. Okay, so something else that we've heard a lot about today is periodic resolutions of algebras and twisted periodic resolutions. So, okay, I think, I'm not sure if anyone's written this down, but certainly many people have said it out loud. There's this famous theorem of Brenner, Butler, and King, which tells us how the preprojective algebra works in Vinci type from a homological perspective. It says if Q is Vinci, then its preprojective algebra is twisted periodic, period 3. Okay, and it turns out by some difficult calculations that they did that the twist has order 2, and so it's genuinely periodic at period 6. But for me, this is good enough. I just care that it's twisted periodic at period 3. Okay, so what does this mean? This means there exists some automorphism Q0, which is the vertices of my quiver, such that if I take a simple module of the vertex I, then I start forming a projective resolution, then the kernel is going to be the simple module associated to the automorphism applied to this vertex. So this means that this is exact, where there are zeros starting it. Okay, so there's a similar result in the higher case. So in the higher case, we have results. Okay, so for D equals 2, a lot of this was done by Evans and Pugh. Again, we've heard about this just now and earlier. This is also done by Dugas for general D, and we have some different explanation using the higher AR theory. And this says that if we start with an algebra lambda, which is D representation finite, so there exists one of these D cluster tilting modules, then we get the preprojective algebra of lambda is again twisted periodic. Now the period, just what you might guess from here, it's d plus 2. Okay, so I mean, some of the difficult things about the Brenner-Butler-King and the Evans-Pugh results is that they generally show that this twist, this automorphism, has finite order. And I think Kevin Urban talked this morning about the problem of this problem in general, that twisted periodic doesn't imply, we don't know it implies periodic. And I mean, so for this reason, we can't say some precise periodicity result about the algebra having a periodic resolution of bimodules. But we can say twisted periodic. I mean, this partly goes by sort of following the ideas in Brenner-Butler-King, some of which going back to Crawley-Bovey and Schofield and Ringel. Okay, so
So you're effectively using the theorem that Karen said, that if you have this bijection on simples, you will have some automorphism of the algebra.
yeah.
In the algebra case, you just don't know how to control it.
Yeah. Okay, so an application of this. So we also get from this that that these algebras. Okay, if I also if lambda is d-representation finite, and also we start with a causal algebra, then we get that the higher preprojective algebra is almost causal. Okay, so this gives lots of new examples of almost causal algebras. So, in particular, if we take these higher type A algebras, then we can vary D and S. Then we can, I mean, there are these parameters on the almost causal algebras, which are roughly how long the initial segment of the resolution is, and then how far you have to jump down before starting to do it again. And I think we can get either of those to be anything we want just by varying D and S. So this gives lots of examples of almost causal algebras. Okay, so okay, so something else that Alistair mentioned earlier is if we have A, which is an algebra, K algebra, then we can form a new algebra from it. This is the trivial extension. So this is just as a vector space, we take A direct sum A star, where A star is what some other people were calling dA. It's really just the dual space, the linear functions. Okay, and so that tells you what it is as a vector space. I should tell you how to multiply elements. So if I have an AF, so A is in A, and F is a functional on A, and then I have some BG. Then in the first coordinate, we just multiply them. And then in the second one, we use the fact that the dual of A is an AA bimodule. We've seen this a lot before today in the definition of Frobenius algebras. And so we can act on F by B, and we can act on G by B. Okay, so, and now remember that, that the definition of a Frobenius algebra is that on one side, if we take the dual, we get something isomorphic. And okay, you have to check something a bit, but you can guess that if we take the dual of this, we're going to get something that looks like this. So this is Frobenius. And this is always Frobenius. And in fact, it's more than that. It's symmetric, which just means that this Nakayama automorphism that Matthew was talking about is just the identity. Maybe I'll write identity. Okay. So a nice thing that, again, Alistair mentioned just now is that if Q is bipartite, its underlying graph is bipartite, then algebra Q, or KQ, and the trivial extension of KQ are quadratic dual. Okay, so roughly what this means is, we've seen the relations to the preprojective algebra, and they're quadratic, they're homogeneous at degree 2. We take some orthogonal space of relations. I mean, I should take some dual spaces to do this properly, but we just take orthogonal relations. And so one way to write this is the pi of KQ, and you put this little shriek here to mean quadratic dual, is isomorphic with K. Okay, so this was, notice that by this shriek I don't mean causal dual, because these algebras aren't causal, they're almost causal. So I really just mean do the stupid thing and take the quadratic dual, which you just sort of do by basic linear algebra. Then, okay, one thing that's, well, at least within the paper, the motivation for the work of Brenner Butler King was that, after they get the minimal resolution of pi as a binodule, which is great in itself, they then use this almost causal duality to get the minimal resolution of the trivial extension algebra. And they get some periodicity result for this. Okay, so I want to start jumping about a bit now. So I've said a lot about preprojective algebras, but there's also this word zigzag algebras in my title. So at least this name was invented by Huefrano and Khovanov, again around 2001, something like this. They define the zigzag algebra of a similar graph G. So, one way to describe this, and this is in their paper that this is equivalent. So we take G, and then we get a quiver by taking an orientation. And then we take a trivial extension of KQ, where we mod out by all paths of length at least 2. Okay, so we can call this Z of G, the zigzag algebra of G. When you need to check this doesn't depend on the orientation, but it doesn't. Okay, so why is this called the zigzag algebra? So they don't explain this in the paper, but I think it's not too difficult to guess why they called it this. So let me do some example of a zigzag algebra. Well, the quiver looks a lot like these preprojective algebras. These ones over here are examples of zigzag algebras. So, okay, so if we start at some internal vertex, vertex 2, say, then there are two ways to go from 2 back to 2. I can go via 3, so I can zig here, and then I can zag to go back to 3. Or I can zig to 1, and zag back to 2. So in their definition, these are defined to be equal elements of the algebra. They have this relation that if you zigzag one way, it's the same as zigging then zagging the other way. Okay, so why did they care about these algebras? Well, they were interested in categorification and quantum groups. So, first I should tell you a remark. If Q is ADE, then this definition is slightly nicer because the preprojective algebra is isomorphic to the zigzag algebra for any orientation. Okay, so what Huefrano and Khovanov wanted to do was to categorify some representation, the adjoint representation of the quantum group, and this is UQ of the Dinkin type of the graph. So G is still a Dinkin graph. And to do this, they used the divide category and these so-called spherical twists. So, as well as these authors, there are various other people, Seidel Thomas, Rukia Zimmerman, and there's also a Khovanov Thomas paper, but I've written all those names down already, so maybe I would write that. So these are some functors going from the derived category, the zigzag algebra of my graph, to itself. And these are auto-equivalences. So I, the vertex, and there's not lots of nice things about these auto-equivalences. So the famous one is that they satisfy grade relations. So here we get grade relations. So for example, if I and j are neighbors in the graph, then we get this minus 3. And this is, we also get some commutativity for far apart vertices. Okay, so these are, if we look at these two things, maybe I and j are 1 and 2, then these are just two different ways of writing down the longest element of the symmetric group. Okay, so these are two expressions. The longest element W naught. The symmetric group S3 lifted to the break group. Okay, so so we have the break group on 3 strands, which is just generated by S1 and S2. Want to know this relation? We map the symmetric group, which is just the break group modulo. But if we do one of these twice, we get the identity. Okay, and so if I have some longest elements in here, maybe I'll also use notation and write it as W naught there. And I want to take some positive lift. I mean, there's some choice about plus or minus ones in powers because of this SI squared. Okay, and a nice property of the longest element is that, okay, so if we look at W naught squared, this is S1, S2, S1 squared, and this is, okay, so this is 1, 2, 1, 1, 2, 1, or 1, 2, 1, 2, 1, 2. This is S1, S2, power 3, which is just the Coxeter element to the power of the Coxeter number. Okay, so encompass two elements, S1, S2, and H plus the number, which is 3. And these longest elements have some nice interpretation on the derived category via this breakthrough action. So, Rukier and Zimmermann showed that that in type A, the action of this longest element on the derived category comes directly from the periodic, the twisted periodic bimodule resolution of this zigzag algebra. Okay, so this is nice. So I want to press this connection between the preprojective algebra and the zigzag algebra. So note that in general, preprojective algebra is not quadratic dual to the zigzag algebra. I mean, there's two things that go wrong here. This fails in small cases, which is sort of exceptional, but in particular, if we will move outside of AD, for example, if I take a triangle, then we really do get non-isomorphic algebras. So it would be nice if we could fix this. So let's have an algebra which has global dimension D, which is finite. Then I want to define some variation of the trivial extension. So I'm calling these S-triv. The S is meant to be something like super. We're not quite sure what to call this yet. So again, I want the same underlying vector space, but now I just want to introduce some sign, some little twist. If I multiply AF by BG, I want to get AB, and then I want to get FB plus minus 1, the ID, AG. Okay, and this is for A belongs to the certain graded part. Okay, so this is A belongs to lambda I. So, okay, for this to make sense, I need lambda to be graded. Okay, so then we can really fix this. We can really fix this quadratic correspondence between the preprojective algebra and the zigzag algebra. Okay, then for any cyclic Q, if I exclude these two examples at the bottom of type A1 and A2, where something a bit weird happens, then we really have that the zigzag algebra. We really have the preprojective algebra is quadratic dual to the this graded trivial extension of now the quadratic dual of the path algebra. Okay, so from here we might want to make a definition and say that if we have lambda causal graded, this global dimension is D, and I also want some other condition. I also want that x cubed. So this is for I between 1 and d minus 1. Then we can define a higher zigzag algebra. By just taking this graded trivial extension of the quadratic dual of lambda. Okay, so note that from what I said earlier, this doesn't agree with the Huefrano and Khovanov definition in the case d equals 1, but it does agree in all the cases they actually wanted to use it in their paper. And there is some history of people using these sort of different signs. I mean, they predicted this in their paper and they defined them and called them skew zigzag algebras. So now this isn't completely consistent with their naming, but I think it's good because we have some nice results, in some cases. So we can show that there is a surjective algebra map under the assumptions in the definition, from the quadratic dual of the preprojective algebra to the zigzag algebra. And if we really look at these higher type A examples, and this is an isomorphism if S is at least true. Okay, so this is the analog of excluding these A1 and A2 cases from before. So we really, so in this case, the higher preprojective algebra and the higher zigzag algebra form an almost causal dual pair. So, okay, so let's have some example. Like take the zigzag algebra of lambda 2, 3. Okay, and okay, now if we start at some vertex, I mean we can zig away from it, and we can zag, but then to get back we have to also resolve. And there's different ways we could do this. I could take the same zig, then I could zag over here, resolve over here. So we could call these zigzag zog algebras, but the naming gets difficult as d increases. These are quite nice algebras. I mean, they're nice to play with. I like finite dimensional algebras, and these seem to be quite fun. And we do get some interesting things on the derived category. Okay, so again, there are spherical twists at the vertices. Okay, so we still have these relations, this y minus 3. We have if I and j are joined by some edge going in either direction. But we in fact have more, so we could imagine some analogs of braid groups. I mean, I don't know if this has anything to do with braids in a real sense, but it's the analog of the thing that acts in smaller dimensions. So the vertices of the quiver. We have some relations which say that SI1, SI2, SIN, SI1, and you just rotate it by one place. SI2, SI3, SIN, SI1, SI2. So the beginning and end always match. And you're allowed to do this if you have cause the cycle in your quiver. Okay, and then we do get some action of this group on the derived category, the zigzag algebra of this higher type A. And okay, this. So a nice thing I'm just literally rubbing out is that in the classical case, these longest elements have some nice interpretation, and we do get something like longest elements. So there are analogues of longest elements. So, for example, in this case, Z23, then I could define my longest element to be 1, and maybe I'll just write the numbers. X, 1, 1, 2, 3, 4, 5, 6, 1, 2, 3, 1. Okay, these should all have F's above them. And the action coming from twisted bimodule resolution. And so these are very nice functors, these compositions, and we get some relations between some compositions of spherical twists. And I wanted to say something about the these Coxeter numbers, just because they came up in Allison's talk, and I didn't realise that there were these Coxeter numbers in these higher cases. So it will be interesting to see if these Coxeter numbers behave in the same way. But at least in one example, I could calculate between these two talks. So say there's 2, 2, which just is a triangle. I mean, it's very easy. Then we really do have this longest element is 1, 2, 3, 1. And what I'm calling a longest element. If I cube it, then I really do get 1, 2, 3, 4, where C is like my Coxeter element. I take one copy of each of the vertices and multiply them together. I don't know if this works in general, but this seems to work here. And there was one more thing I wanted to say. What was it? Okay, I can't remember what it was. So that's it. Thanks for listening.
Okay, thank you. Any questions or comments? No comments, no questions. So let's think and all speakers